start our little recording. Whoops. Okay. So, everyone got assignment 2? Everyone's handed in assignment 1, looks like. Looks like I got a decent pile here, so that's good. Can't wait to mark them all. No, I'm just complaining. They'll all be perfect, I'm sure. So assignment 2, again, you're just gonna do it on here, hand it in. It won't always be like this. I know, I'll say that now, but you just handed one in, you get one back, but it's because chapter 2 is so short, right? We're only spending last day and today on it, so here's an assignment. Okay. Did anyone not get a formula sheet last day? I've got a few up here. They're used, Anyone else need a formula sheet? If you need one, you can grab one after class. So, did anyone not get the chapter 2 handout last day? Just get one. Everyone else has one. It says chapter 2 on the front. Probability theory. Great. Okay. Not bad. Not bad. So just a quick review. Right. It was just on Monday, so we don't have to review it too much. Is it too bright for you guys? Can you see the screen, or is it? It's okay. Top notch. So we started chapter 2, which is this kind of separate chapter where we do probability. We'll be doing probability throughout the course, but it won't be like this. Okay. Is that my phone? Could be, but I don't think so. I'm pretty popular. So, I know the assignments do. Can you here's some pictures? Just yeah, you got it. Right, that's what we said. So if you, for some reason, can't make it to hand in your assignment on time, you still have to send me pictures, kind of proof of life pictures, if you will, before it's due. Okay, so you can do it. So we talked about probability. What is probability? We talked about probability notation, probability facts, right? Probabilities have to be between 0 and 1. And they all have to add up to 1, right? If we're talking about the whole sample space, which is the list of all possible outcomes, there's a lot of terminology that we introduced. And that's why I gave you this printout. I kind of just put everything on a sheet, kind of first draft here, but it's all there, so that's good. And so we talked about what does it mean for events to be disjoint, right? It means that they can never happen at the same time. And then how do we calculate probabilities when they're not disjoint, right? Here we have this situation where we had 2 events that are not disjoint, right? Face cards and diamond cards. And we developed this general formula, which is on your formula sheet. Right? The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And we said, and what we'll see on the assignment, but also today in the example, is that as long as I give you 3 of these 4 things, I can ask you to solve for the 4th one. We talked about probability distributions. Right, a probability distribution is the list of all the possible outcomes. They have to be disjoint, and their probability is listed below. Again, we have to make sure that all the probabilities are between 0 and 1, and they have to add to 1, yes.
When you say minus the probability of A and B, what is the and?
So I would give it to you. So the probability of this and this happening is, and I would give you a number.
So, I don't know, I'm thinking, is it times or, I'm thinking within that line.
It is. It is multiplication, but we have to be careful, and we'll talk more about it, and you'll see it in an example. But if it's still hazy, then let me know. But it is multiplication, sort of. Yeah. Is there a question in the back? Or? Oh, okay. Nice. So we talked about probability distributions. And then yes. We'll talk about Venn diagrams in just a sec too. But we won't, yeah. We're not going too deep into this chapter. As you can tell, we can broaden our horizons however wide we want to. Okay, but we're just gonna touch in, touch out. So we might not get to the multiplication thing, and at least not the theory. And then just before I let you go last day, I said, oh, and here's a complement of an event. It's just the opposite of it happening. And then you guys left and forgot all about it. So let's just talk briefly about the complement of an event. So the complement of an event is just the opposite of that event. So if you're rolling a die, for example, then let's say the event of rolling a 4 or a 6 is B. Remember, this is set notation, which I don't expect you to know, but we can read it. That's fine, right? 4 or 6, that's B. So then not B is the complement of B, which is B just with a superscript C, or even prime, or a little apostrophe if you want, which I tend to go for. If I'm writing quickly, I'll just do B prime. But we have complement on your formula sheet, and so I try to stick with that. But if you see B prime, they're the same. And if you want to use B prime, go for it. But the complement of B then would be 1, 2, 3, and 5, right? So everything that's not 4 or 6. Okay. So that's the complement. And if I told you, trying to scroll on here, if I told you the probability of picking a male is 0.8, what's the probability of picking a female? 1 minus 0.8 is 0.2, right? So we have a pretty good understanding of how complements work just kind of in life, right? And so here, the probability of not A is just 1 minus the probability of A, which I think we're all kind of okay with, but here it is in mathematical notation, and that's what's on your formula sheet. Okay. So, any questions about that? Cool. Let's talk about independent events. Let's zoom in a bit here. So, independent events are any two events that, knowing the outcome of one, has no effect on the probability of the other, right? So for example, knowing that I flipped a coin and I flipped it 4 times and all 4 times were tails, for example, that has no effect on the probability of a tails for the next one, right? Despite what we might want to think, right? But it actually has no effect on the next outcome, right? And so those two events would be independent. Of course, a lot of things are not independent. And here's kind of a weird thing. Not independent, we could call it dependent, but for some reason we don't. I wasn't taught, I was just taught it's either independent or not independent. And so we didn't call it dependent. You're welcome to call it dependent if you want, but I'll stick to independent or not independent. Don't know why, but just kind of a quirk, I Yes. So some things that are not independent, and these are really kind of common things that things aren't independent. Stocks, that's a big one. Right? Stocks go up, they all kind of go up together, or vice versa, right? If there's something that's kind of working against it, right, then as one stock goes up, another one goes down potentially, right? So either way, they're not independent. Weather, right? Knowing the weather today affects the probability of the weather tomorrow, right? So knowing that it snowed today affects the probability of it being 30 degrees and warm out tomorrow, right? Very unlikely. And so another really common scenario is disease, right? Knowing that one person at the school has H1N1, for example, means we all have it. We're all sick. Just trying to think of a common school illness. Strep throat. No, I went for H1N1. The flu. Common flu, right? And so knowing that someone on campus has this illness, right, the probability that you'll get it is much higher. Right? Even genetic diseases, right? Knowing that your parents have some genetic disease, the probability that you'll have it is much higher than someone whose parents don't have this genetic disease. Right? So those are all not independent. As you can tell, it sounds like just about everything, right? Even cards, right? Knowing that I've pulled up 2 red cards already, that affects the probability of drawing another red card, right? As long as I'm holding them. So a lot of things are not independent. We have a check to see if 2 things are independent. Okay. And this is the one that's on your formula sheet, and it kind of wraps up the chapter 2 section, although we haven't seen all of those yet, doing them out of order. If A and B are independent, it's on here too, but it's kind of snuck in here. So if A and B are independent, then the probability of A and B is going to be the same as the probability of A times the probability of B. That's only true if A and B are independent. Okay. So I'll just highlight that here. So we can use that calculation as a check rather than to calculate the probability of A and B. As long as we have each of these 3 pieces, we can check to see if A and B are independent. And so if they're not equal to each other, then they're not independent. Okay? So let's see here if I had any other notes, or if I'm just blabbing at you. Probably just blabbing at you. Nope. So let's do a little example. This one's actually more, a little bit more advanced than what you'll see on the assignment and on the test, because on the assignment and on the test, I just give you the probabilities, right? But it's this is also an exercise in trying to figure out what the probabilities are, right? And so the example is in a math class of 30 students, 17 are boys and 13 are girls, right? And so using that, we can find the probability of picking a girl, the probability of picking a boy. On a unit test, 4 boys and 5 girls made an A grade. Doesn't really make sense to me, but that's what copy and pasting will do to you. Made an A grade. So then we can answer all of these questions, and we will, right? But here, it kind of makes us develop these probabilities, which again is not something that I'm expecting you to do on a test, for example. I would just give you the probabilities. Let's call this is actually 2.1 example 1. Oops. I stole this question, and I also stole this image because I thought it was so cute. I also stole the other question, not as cute. So, we want to know, so if a student is chosen at random from the class, what is the probability of choosing a girl, choosing an A student? And so I've just made some room here. And I'll do 2.1, example 1. First thing I'm going to do, right, because I want to use these shorthand A, B, right? And so I'm going to pick letters that are kind of more appropriate for this question, right? So I'm talking about picking a girl, and if we read on a little bit here, we'll talk about, we want to know about the girls and the A students, right? And so what I'm going to do is I'm going to let G be choosing a girl. This way I don't have to write that out every time. I can just say G, and it takes the place of choosing a girl. Saves us a lot of writing. And A be choosing an A student. So question 1 was, what's the probability of choosing a girl? So if we translate this into probability notation, we get P of G. Well, there were 13 girls and 17 boys, so the probability of choosing a girl is 13 out of 30. Or if you prefer as a decimal, which typically I would like decimals. I don't know. I don't like to deal with fractions. I'll show you this one with fractions. But in general, I'll stick to decimals. Thanks. Okay. The probability of an A student, right? We said 4 boys and 5 girls got an A. Right? And so a total of 9 students got an A. So 9 out of 30 students, or 0.3 if you prefer. So, any questions so far? So far, so good. It's good. Question 2. Draw a Venn diagram of the 2 outcomes. So, how am I supposed to do that, Emily? You haven't shown me how to make a Venn diagram. I am kind of assuming that you've seen one as they make pretty good jokes. So you've probably seen one somewhere along the way, right? But a Venn diagram just looks like this. So we start with, I almost said a square. It's not a square, it's a rectangle. Picky. This represents the sample space, right? All possible outcomes go in this rectangle. Okay. And then because we have 2 outcomes, we have 2 circles with some overlap. And here's a Venn diagram. So what you're gonna do is you're gonna label each circle with whatever you're interested in, right? Picking a girl, picking an A student, right? And so what we've got here is everything in the G circle. Those are all your girls. Everything outside of the empty circle, those are all your boys. That'll make up the whole sample space, right? If you've accounted for all your girls and all your boys, they're all in there, all 30. Here's all your A students. Outside of that is all your non-A students. Here's a little bit of overlap. All those girls that got, or all of those girls, the girls that got A's. So what's outside here? Well, it has to be all the boys for sure, right? But it's also all the boys that didn't get an A. Right? So out here, in this white space, right, we've got all the boys that didn't get A's. Right? Here, in this kind of half moon area, you've got all the A students that are not girls. And so we can extract a lot of information from this graph, but first we're gonna put all the, what each portion is worth. Okay? And you can do that in terms of probabilities, so decimals, or I'm gonna stick to the fractions for now. Okay? And so I'll just label each portion. Right? It's always a good idea for Venn diagrams, if you're drawing them and you're trying to figure out what to put where, it's a good idea to start in the area with the most overlap, right? Because we could have 3 circles, so then you'd want to start and fill in the area with all the overlaps. Okay? And so here, and I'll show you why, or you'll see why in a sec. This area is worth 5 out of 30. Okay. Those are, we had 5 girls that got an A on the test. Okay. Overall, we know we have 13 girls, right? So if we had to figure out what that G, I call it a half moon, I don't know, portion, sliver, whatever you want to call it, right? If we want to know what that area is worth, so this area here, that's going to be 13 minus the 5 that are already counted, right? And so that makes 8 out of 30. Same idea here for the A sliver, half moon. Those are all the A students that are not girls, and that's just going to be 4, right? There's 4 boys that got A's. So 4 out of, oops, 30. Just like all the other sample spaces that we've looked at, right? Probability distributions, all these things, the total of all these areas has to add to 1, right? So we could think of it as, okay, well, this outside area, that's all the boys who didn't get A's. So we could count them, right? 17 minus the 4 that got A's. So that's 13. Or we could just say, well, they have to add to 1. And so 8 plus 5 plus 4 plus something has to add to 30. Either way, you're going to land at 13 over 30. So now we've got probabilities associated with all these areas. It makes it a little bit easier to answer questions. So on the assignment, where do I have a copy? Here. Question 1B, I just tell you to use a Venn diagram to find the probability of seeing a whale but not a dolphin. So I'm not expecting to see any calculations there. I just want to see your Venn diagram, and did you use your Venn diagram to figure out which area you wanted? Okay. That's good. But for this question, I think I just said, oh yeah, draw a Venn diagram of the 2 outcomes. Great. Any questions about that one? So what's the probability of choosing a girl who got an A on the test? And so we want the probability of choosing a girl who also got an A on the test, which is basically G and A. G and A. We could just look at the Venn diagram, and if I've asked you to make a Venn diagram, you can just use the Venn diagram to answer the questions. So it's 5 over 3, or 5 over 30, sorry, or 0.16 repeating. And I can just say from Venn diagram, oops. What the? That's fine. 4. What's the probability of choosing a girl or an A student? So a girl or an A student is going to be a little bit different. Yeah, we'll talk about it. So the girl, right, or an A student. So now, whenever I say or, it doesn't matter which one, as long as it's one of those, right? So that means you could be in the G circle or you can be in the A circle. And so one thing that you could do, right, if you've mapped out all your probabilities, is you could just say, well, that should be this area plus this area plus this area, right? Or if you want to get creative, you could say, well, the total probability has to be 1. So it must be 1 minus this outside area, is everything in that little bubble, right? So there's lots of ways that you could go about doing it. For us now, we're going to use the formula, right? Because we know that the probability of A or B, right, is the probability of A plus the probability of B minus the probability of A and B. And we have all those probabilities, right? We have the probability of G, we have the probability of A, and we have the probability of G and A. Right? So we have those 3 pieces that we need to find the probability of G or A. So I'm going to use that route. But you'll notice that it doesn't really matter how you do it, as long as you show me what you're doing. Doesn't matter. So it's the same as the probability of G plus the probability of A minus the probability of G and A. Probability of G is 13 over 30 plus the probability of A was 9 over 30. Minus the probability of G and A is 5 over 30. Like I said, I don't like fractions more than anyone else. So I'm just using them now because they all have the same denominator, right? So I don't have to find a common denominator. So it's easier to work with these fractions. But if you wanted to work with just the decimals, that's fine too. What we'll find is that this becomes 17 over 30 or 0.566 repeating. I'm gonna have to add another page here. Which I had to Google before this class, how to do. But now I know. Look at me go. So, this would be the same, right? What we did here was we're essentially taking the whole G circle, right? 13 over 30, the whole G circle plus the whole A circle, 9 over 30, and then subtracting the overlap once. That's the same idea that we had before, right? Where we had that overlap, we had to subtract it once. So it works the same way. How about 5? Are choosing a girl and choosing an A student independent? Right. Here's where you have to, and I ask you this on the assignment, right? Part C, so question 1, part C. Are seeing a whale and seeing a dolphin independent events? Justify your answer mathematically. Okay. So 5. Are G and A independent? G and A are only independent if the probability of G and A is the same as the probability of G times the probability of A. So what I'm going to do is I'm going to put a little question mark up top of the equal sign because I'm not sure. I'm just checking if they are equal or not. But I have all these probabilities, right? Even if they're fractions, it doesn't matter. So I've got 5 over 30. Does it equal 13 over 30 times 9 over 30? Something tells me no. Here, if I convert this to a decimal, 0.0166, is it equal to 117 over 30? Or sorry, not over 30, over 900. .166, repeating, is not equal to 0.13. So because they're not equal to each other, they're not independent. So we can justify it here and say, since the probability of G and A does not equal the probability of G times the probability of A, the events G and A are not independent. So if you have to find the probability of A and B in general, right, you can't just multiply the two together necessarily, only if they're independent, right? We'll talk about how do you do it in general, but this is a special case when A and B are independent. So, any questions before we do that second example? So, I'll just put in a little label on here. 2.1 example 2. I guess there is some space for it after the questions, but I'll leave it. Now I've got this blank page to work with. So on New Year's Eve, the probability of a person having a car accident is 0.09. Okay. The probability of a person driving while intoxicated is 0.32. Yikes. And the probability of a person having a car accident while intoxicated is 0.15. Yikes. The first question I've got on there, I actually want you to cross out. We're not going to draw a Venn diagram because it doesn't work. Because I was working too fast. Just just copied and pasted the questions. But because the probability of having an accident while intoxicated, it depends on if you're intoxicated or not, so it doesn't work. But we can do all the rest of the questions. So I guess I'll just do them. Where am I going to do these? How long are they going to take? I'll just do them below here. So 2.1, example 2. So we're talking about two things, right? We're talking about, what are we talking about? Driving while, or having a car accident and driving while intoxicated. Cheerful topics. So let A be having a car accident. And let I'm just picking whatever letters kind of make sense to me at the time. I be driving while intoxicated. Notice that as a general rule, I just use capital letters. So you want to try to use capital letters, but you can pick whatever letters you want. So now we've defined these, and now we can just use those as shorthand. So question 1, or I guess 1, don't do 2. List the 3 probabilities given using probability notation. Right, this one's nicer because I just give you the probability is this, the probability is that, right? And so you don't have to try to figure out what those probabilities are. And that's more like what you'll see on the assignment and on the test, right? Just give it to you. So we have the probability of A, right, having a car accident is 0.09. The probability of I, driving while intoxicated, is 0.32, scary. And the probability of A and I, 0.15. So those are the 3 probabilities that I've given you. Question 3. Are having a car accident and driving while intoxicated disjoint events? Disjoint, remember, means that they can never happen at the same time. But we also said that 2 events are disjoint if the probability of one and the other is 0, right? That means they can never happen at the same time. So you could, there's 2 ways that you could go about answering this question. You could argue that no, they're not disjoint because they can happen at the same time. That's fine. But a little bit more powerful would be to say, no, they're not disjoint because the probability of A and I is 0.15, which is not 0. And so they are not disjoint, right? Kind of back it up with the math. So we can say, since the probability of A and I is 0.15, which is not 0, these events are not disjoint. These events are not disjoint. So just have a look. Is there a probability of them happening at the same time? If there is, then they can't be disjoint, right? Because there's a probability that they'll happen at the same time. 4. What's the probability of a person driving while intoxicated or having a car accident? So now we want to know what's the probability of I or A. That's the same as A or I, right? They don't get thrown off just because we have the probability of A and I, and later on here, we'll need the probability of I and A. They're the same, right? You can switch them. So this is the probability of I plus the probability of A minus the probability of I and A. Right. So I just follow the same setup, right? First one, second one, minus first one and second one. Right? Kind of same rhythm. So here, the probability of I is 0.32, plus the probability of A was 0.09, minus the two together, 0.15. So the probability of both of them, or I or A, I should say, is 0.26. I shouldn't have written so lofty. I only have that much room to write out question 5. I think I can do it though. Well, maybe I'll just move this up a little bit. Nice. Are having a car accident and driving while intoxicated independent events? Let's find out. So, if having a car accident, so if A and I are independent, right, then the probability of A and I must be the same as the probability of A times the probability of I. This is easier than those fractions, right? Because we can just use the decimals right away. So we know the probability of A and I is 0.15. Is that the same as the probability of an accident, 0.09, times I, 0.32? 0.09 times 0.32 is 0.0288, which is not 0.15, meaning they're not independent. Therefore, A and I are not independent. Neato burrito. Nice. There's one quick little note, because it's hard to kind of keep track of the disjoint and the independent. But one thing to keep in mind, so disjoint is talking about the actual outcomes, right? Can this happen at the same time that this is happening? Right? Whereas independence is talking about the probabilities, right? So is the probability of this, does it depend on something happening, right? Or knowing the outcome of one other thing. So just as a little note, disjoint refers to the actual outcomes. While independence refers to the probabilities. Just to try to keep those straight a little bit. Any questions about that section before we move on? Okay. So basically, what happens when they're not independent, right? Then how are we supposed to calculate the probability of A and B if we're not given that value, right? And so we need to develop some general ways of finding it. Okay? But first I want to have a look at, so we've seen a contingency table like this. It was all ugly, right? It was from the R output, so it didn't look nice like this, but we've seen something like this before, right? Where we're comparing two categorical variables. In this little example, we're looking at, so here we consider a sample of 792 teens. We're college, right? Here's the college, no college. Where college means the teen went to college immediately after high school, right? So are you going to college right away? Yes or no? Yes, college. No, no college. Doesn't mean they're not going, it just means they're not going right away. So, and then the degree variable indicates whether at least one parent has a degree. Right? Do either of your parents hold a degree? Yes, degree. No, no degree. Right? And so we can split up our sample. Right? We have 792 teens, so that's our total sample size. And then we can break up by these two categorical variables. And so we're going to let D represent at least one parent has a college degree, and C is the teen went to college immediately after high school. Now we can use this table to answer some probability questions. Just to get started, reading these tables a little bit more thoroughly than we have been. I guess I should make a note to call this 2.2 example 1. What proportion of teens have at least one parent with a college degree? And so here we're just talking in general, out of all these 792 teens, how many D's are there essentially? Right? And so it doesn't matter if the teen went to college or if they didn't, right? We just want to know out of this sample, how many had at least one parent with a degree? 280. Right? And so we have these totals out in the margins that we can use. And so let's see here. I think oh yeah. 2.2 example 1. The probability of D in general is going to be 280 over 792, or 0.3535, repeating if you want to. Question 2. Now we change it a little bit, right? So given at least one parent completed a college degree, what's the probability that the teen went to college right after high school? So now we're saying, okay, given this information, so you know that at least one parent has a degree. Right? So what that means is you're zoomed in here, right, as your sample size, right? Because now you're looking only at these 280 students instead of all 792. So now your total is out of 280. And so given that at least one parent completed a college degree, what's the probability that the teen went to college? And so out of these 280, how many went to college? 231. So what we can say is scroll down here, we can say that the probability of that someone went to college, C, given D, right, that their parent, at least one parent has a degree, is 231 out of 280, or 0.825 if you like. So this idea of given some information, what's the probability of finding another thing? That's conditional probability. So here, this is conditional probability. So then, 3, given that a teen is randomly selected and she did not attend college right after high school, so that's, now we're zooming in on everyone who didn't go to college right away, right? So this is now our total, 347, which means we only have these two to choose from, right? Everything else is out. What's the probability that at least one of the parents has a college degree? So given not C, what's the probability of D? So really, we can kind of flip those and say, well, what we're interested in is actually the probability of D given not C, or the complement of C. We saw that's 49 out of 347, or 0.141210,375. Prefer. You can round those. Just wanted you to have all the values. All right, so just going back to the table here, right, we said, well, out of these 347, 49 of them have at least one parent with a degree at home. This is all fine. I'll scroll back down here. Finish copying. It's all fine when we have manageable tables, right? This would be a 2x2 table. That's fine, right? These things quickly get out of hand. And so, of course, we have formulas for dealing with these things. But if you prefer to look at the table, right, and use that instead, go for it, right? So if you don't like the formula that I'm about to give you, that's fine, right? As long as you can use the table, because we're not going to go beyond a 2x2 table on a test, right? Max out at 2x2, also min out at 2x2. It'll be a 2x2. Anything smaller would be kind of pointless, right? So these conditional probabilities, scroll up a little bit, you have this formula instead. Right? So like I said, you can either use the table and try to figure out, what's going on, or we can use this formula. So one heads up is you've got the probability of A and then a vertical bar, B. You read this vertical bar as given. So that's shorthanded. We don't like writing anything. Probability of A given B. So let's make a note of that in here. So here you've got given. And that's the one that's on your formula sheet. Right. Actually above the independence one. I think my reasoning was because there was text after or in front of the independence one, so I didn't want to run into another formula, because this one applies even if they're not independent. Confusing. Doubt you care. Just put them on there. Yeah. So the probability of A given B, whatever those two things are, is going to be calculated as the probability of A and B. We've seen that before, and we're probably pretty comfortable with that, right? The probability of A and B divided by just the general probability of B. So it's actually not that bad to calculate. And here you've got your probability of A and B. So you can rearrange this to get the probability of A and B is the probability of A given B. Multiply both sides by the probability of B times the probability of B. And then you have this general formula for the probability of A and B. Just a quick little caveat. Right? We said if A and B are independent, then the probability of A and B is the probability of A times the probability of B. What happens to the probability of A given B if A and B are independent? Well, then the probability of A doesn't care what B is. So the probability of A given B, if A and B are independent, it's just the probability of A. Voila, you're back. Don't worry. Just wanted to throw it in there. Fine. Okay. But same idea. So if A and B are independent, then you're back to that special case that you have on your formula sheet. But in general, we have to use the conditional probability in our multiplication. Any questions about that one? Yeah.
If A given B, would that be the same as if B then A? In terms of
Yes. I do say that sometimes, so should be. Any other questions? Ooh. Actually, it would be if B then A. Is that what we said? Yeah. Okay. Good. Nice. So, because we've got these probabilities here, right? Probability of A and B, we could go ahead and convert the table that we've been looking at into probabilities, right? Just dividing each of them by 792 to get probabilities, and that's what I've done in the table down here on the next page. Oh, maybe not. Here. So now these are all probabilities, right? It's the same table. I've just divided by 792, the overall sample size. And now we have this probability table of all these outcomes. One thing to note is that sometimes I'll talk about the marginal probabilities. The marginal probabilities are just the probabilities in the margins. I know, wild, right? So here, these are what I call the margins, the totals, and those are your marginal probabilities. Here in the body of the table, you've got your joint probabilities, right? Because this value is from this one and this one, right? The joint probabilities. So let's just, I'll have to zoom in. I ended up kind of overlapping some numbers earlier, so that's probably not ideal. I want to be able to see those numbers still. I did it again. So this here, these are your marginal probabilities. Use a slightly different color here. And these values inside the body of the table, these are your joint probabilities. It's just some terminology, but can be really helpful. So just as a little example, right, comparing these two tables for finding these probabilities, if we had to find the probability of C given D, we would say, okay, well, the probability of C given D, scroll up, up, up. For you, it's nice and close. For me, not so much. The probability of C given D, right, so given D means we're out of the 280, and the probability of C then, out of the 280 is 231 over 280. So you could find that probability with just the counts. And that's what we have here, right? 231 over 280, and then we calculate 0.825. Or if we have this probability table, like we do here, then we can apply the formula, right? Because these are all probabilities. And so now we have all these probabilities that we can pick and choose from. And so if we want to calculate the probability of C given D, then we know that that's the probability of C and D. Right? I just remember it as this and this over this. You don't have to remember it, it's on your formula sheet. But it's nice to know your way around. So the probability of C and D over the probability of D. And so the probability of C and D is 0.29. And the probability of D overall is 0.35. So what we have is 0.29 over 0.35. Gives us 0.829, which is slightly different from 0.825. The problem is, it's not really a problem, but the reason is that I've rounded all these probabilities, right? So we can only see 2 decimal places here, and so that's why we have slightly different answers here. As long as you show me how you found your answer, right? Whether it be like this or like this, it doesn't matter, right? I'll know what to expect depending on what you did, right? And so as long as you show your work, then you're safe. Because as you've noticed probably, is there's a lot of ways to do all these problems, right? It just depends on which way that clicks for you. Any questions about that one? So those are quick conditional probabilities. So moving on to tree diagrams here. Often we have to deal with consecutive events, right? On the assignment, in question 2 on the assignment, you've got day 1 and day 2. So you go on a whale watching cruise on 2 consecutive days, right? So you've got day 1, day 2. You pick your first card out of a deck of cards, then you pick your second card out of a deck of cards, right? That kind of thing. So you've got 2 consecutive events. And so the easiest way to visualize those probabilities and like how they behave is with a tree diagram. Really just mapping out the information that we have, and it makes our calculations go much smoother. Much like a Venn diagram, but a little bit more advanced. And so tree diagrams, we've got 2 consecutive events. We'll max out at 2. In fact, a tree diagram ends up looking like option 1, option 2, or yes, no, let's say. And then each branch has its own set of branches after it. Right? Imagine if you had 3 possible outcomes. 3, 3, 3, 3. Gets out of hand pretty quickly, right? So for that reason, I'll just do 2 and 2. 2. So I'll show you by example. 13% of students earned an A on the midterm, and of those students, right, so assuming that you got an A on the midterm, 47% got an A on the final. 11% did not get an A on the midterm, but got an A on the final. And so we're going to build a tree diagram labeling all the appropriate probabilities. What you'll find is once we're done our tree diagram, the rest of these questions, you can just look at your tree diagram to figure them out. Because your tree diagram is going to be a lot of work. Okay. So let's see here. Oops, call this 2.2, example 2. So I'll start on my blank page here, page break. So 2.2, example 2. First thing I'm going to do is just define the events that I'm talking about, right? And so these are two consecutive events, right? Midterm, and then they write a final. It gets tricky, right? Because we're talking about, did you get an A on the midterm, yes or no? And did you get an A on the final, yes or no? So we can't really use A's. It would apply to both. So I'm just going to use M and F, right? A on the midterm is denoted by an M. F, ironically, you got an A on the final. Okay. So a little bit confusing, but let M be an A on the midterm. And let F be an A on the final. So there's only two outcomes at each. I call them layers. I don't know, it's not technical or anything. I just think of it as layers of a tree. And so what we're going to do to draw this is I'm going to start and draw my first two branches. Right? I'm going to call this my midterm layer. I only mention this because you'll probably have questions about the assignment. And when I respond, I'll say, oh, in the first layer or in the second layer. Right? So that's what I mean. Here's the first layer, the midterm layer. And then what we'll have after each branch is another set of branches. This is the final layer. I'll say final exam layer. It's also the final layer. We don't go any deeper. So here, because we're breaking it up as you either got an A on the midterm or you didn't, right? We can say, well, this branch can be M, and this is the complement of M. So depending on how you did on the midterm, this will determine where you go down this tree. Same thing on the final. You either got an A on the final or you didn't. And that applies for both, right? If you got an A on the final or on the midterm, or even if you didn't get an A on the midterm, you could get an A on the final or not. So what we're going to do is we're going to jot down the probabilities on each of these branches. And so where do I have it here? You have it right there, but 13% of students earned an A on the midterm. So the probability of an A on the midterm is 0.13. The complement of that, 0.87. Of those students, so of those who went down the midterm branch, right, the M branch, 47%, so 0.47, got an A on the final, which means that 0.53 of those people didn't. 11% did not get an A on the midterm, but got an A on the final. So 0.11 here and 0.89 if they didn't get an A on the midterm, they didn't get an A on the final with a probability of 0.89. Okay. So what I find really helpful is if I just jot down the combinations that get me to the end of each branch, right? Here's a midterm, here's an A on the midterm, here's an A on the final. So at the end here, I'm just gonna write MF, right? Because that's the combination that gets me to this point, right? So it's essentially M and F. Here, M and not F. And so I'm just cutting out the and. Getting sneaky. So down here, I'm going to write MF, because that's the outcome there. I'll make a note on this one. That's the same as M and F. For the rest, I'll just use this. Yet another shorthand. M and not F. Not M and F. And then not M, not F. For a complete tree diagram, I also want to see the probabilities at the end of each branch. So the probability of M and F, this probability, right, depends on them getting an A on the midterm, right? So this is a conditional probability. Right? So technically we have the probability of F given M, right? But if we're just doing this, right, we don't really need to know the mechanics of it, but it's because this is a conditional probability. But what we're going to end up doing to get the probability of each branch, right, at the end of each branch, we're just going to multiply down, right? Because this and this. And so we can find, I'll show you what's going on. Right? But as long as you remember that, okay, to get the probability at the end of each branch, I just need to multiply down. Right? So this 0.47 is really the probability of F given M, right? Because you had to go down that M branch to get there. Okay. And so I'll show the probability of M and F using the formula, but then we can just skip it and just say, oh, I just multiply down. So that's the probability of F given M, that's the one we have, times the probability of M, which is 0.47 times 0.13, which is 0.0611. Or just multiply down each branch. Save you a little bit of time. So the probability of M and not F, right? That's the second branch that we're talking about, right? So that's 0.13 times 0.53 is 0.13 times 0.53, which is 0.0689. Can keep going. The probability of not M and F is 0.87 times 0.11, which is 0.0957. And then finally, the probability of not M and not F is 0.87 times 0.89, which is 0.7743. Sorry, I'm just cranking these out so you have them, but I'll put them on our tree diagram as well. As far as what I'm expecting to see in terms of work for your tree diagram on your assignment, you don't have to show the calculations. You can just say the probability of MF is 0.0611. The probability of M not F is, what was it? 0.0689. Probability of not M and F is 0.0957. And the probability of not M, not F is 0.7743. If all the students wrote a midterm, right, they can either be classified as A or not A, and wrote a final, not A on the final or an A on the final. So all of these outcomes represent the entire sample space. So one thing that we should check is that this plus this plus this plus this has to equal 1. Right? And so the total equals 1. If you have a peek at the questions, now that we've done our tree diagram, we have all these answers on here, right? And so that's what I mean. So the tree diagram is going to be a lot of work, and the rest are easy breezy. But we'll do those next day. How about? I guess I'll see you on Monday, unless you have a lab at 4. Then I'll see you then. This way? Or other way? I know. It's like, tell me which way to move my finger and I'll do it.
Do you have an extra copy of the second assignment?
I surely do. Oh yeah, if you didn't get the second assignment, make sure. It feels like this is a duplicate. But, there you go. And I've also got another copy of the chapter 2 notes. And also a copy of the 1.7 notes, but those are from last day, so I don't know. Great. You guys got the notes? Okay, I'll post them on Moodle.
1.7 notes?
Yeah.